So a very interesting thing happened when these scientists were looking at radioactive decay and so on. They discovered that the mass of a stable nucleus was actually less than the sum of its parts. And that's why I put here 1 + 1 does not equal 2. This bothered them. It bothered them a lot because we used the conservation of mass for a very, very long time. So what did they call it? They called it the mass defect. Certainly wasn't something they were expecting to have happen. So delta M is the difference between the mass of the nucleons added together and the mass of the stable nucleus made from those nucleons, so that we'll get a positive number since the stable nucleus is less. Okay? We can express it in terms of how much energy it is. This is Einstein's famous E = mc², where there's an equivalence drawn between energy and mass. Before this, we had the law of mass conservation and we had the law of energy conservation, and they were separate. Now, when we start talking about nuclear interactions and so on, we find out that there's an equivalence between them. And so now we say the law of conservation of mass and energy together. But it doesn't come up every day. It comes up when we're talking about things that are radioactive and so on and so forth. So we're going to use this E = mc², and we will call that deficit. And what we get from using the deficit in Einstein's equation, the binding energy. So the mass deficit will be turned into the binding energy. We can call it that and consider it to be the amount of energy that is needed to split the nucleus up. It's a lot like bond dissociation energy, really, but we're going to find out it's much larger. Here's the mass number of all the different elements that we can work with, neutrons and protons together. And what we find is that the binding energy varies a lot as we go through. We don't usually talk about things like this. This is sort of a physics thing, not a chemistry thing. But the strong nuclear force is what is keeping those quarks together in a nucleus. Because we know, based on electrostatics, we know that all those protons hate each other and they don't want to be together. Why are they staying together? Because they're being held together by a different force. Instead of the electrostatics, we're going to be held together by the strong nuclear force. And the binding energy has to do with the strong nuclear force, and we get a rather interesting curve here. We then can see that the most stable thing, the one that we would have to exert the most energy to pull apart, is iron. Everything else is less stable. Over here, uranium that we use in nuclear power plants is less stable. But very interestingly, over here, this is even less stable, it says. It doesn't take much to pull it apart. So on this side, if we're trying to separate them and do things, we would end up doing fusion reactions. If we're trying to do it over here, we end up with fission reactions.